It's what I do for you. So guys, don't write this down, but let me contextualize this for you. So if you remember, the title of chapter 4 is not acids and bases. What's the critical word in the title of chapter 4? Aqueous. This is all about water-based chemistry. Don't write this down. So guys, when we talk about aqueous reactions, we're talking about reactions that occur between ions in solution. So guys, I would propose to you that the critical thought in that second sentence is the word ions. And Catherine dug into this a little bit more deeply when we were grading homework, but let's make sure you're clear on this. Guys, where do these ions exist? Only in solution, and in our class, water. So the idea here, guys, is if something exists as an ion, we understand that it's got to be in water. Okay? So the thought being, and if you're still not clear on this, the idea, guys, is if I give you a pinch of salt, what have I just handed you? NaCl. I have not handed you Na ions and Cl ions. What I have actually handed you is this, which is an NaCl crystal. These things technically right now we don't think of as existing as individual ions because they're bonded to each other in what you'll find out is a crystalline lattice. So what do we have to do to turn these into sodium and chloride ions? Dissolve it in water. Do you get the idea? Okay, and then, so in its solid form, we would represent it like this. In its aqueous form, we would represent it like this. You get the idea? So you ready for a deep thought? You've never tasted salt. You have no idea what salt tastes like. Because guys, the very process of tasting something means you put it on your tongue, and your tongue is wet. And when you put that salt on your tongue, you are not tasting sodium chloride. What are you tasting? Sodium ions and chloride ions. We have no idea what salt tastes like. We know what sodium and chloride ions taste like, but you've never tasted salt. Weird? There you go. So now when your food tastes salty, you can say that it tastes sodium-y and chloride-y. Not bad. All right. Okay, so guys, with that said, let's then talk about where we're at. So we understand, because we overviewed the chapter, that there are three types of aqueous reactions that we're going to encounter in this unit. Precipitation reactions we're done with. Acid and base reactions we'll talk about today. On Friday, we will talk about redox reactions. And then, guys, I will not see you again until the following Wednesday because we don't have school on Monday. And you will take your test over this unit on Wednesday. You good? Okay, no, you're not, but we're going to go forward anyway. So guys, with that said, let's talk about strong and weak acids and bases. So here we go. Guys, first of all, some definitions. And then what you're going to find, and these definitions are a review from last year. But guys, once we get these things defined, you're going to find that everything that we're going to talk about today about strong and weak acids all builds and actually perfectly reflects what you already know about strong and weak electrolytes. So guys, when we talk about acids, you learned last year, acids are substances that ionize in solution to form hydrogen ions. And as they do this, they increase the molarity or concentration of hydrogen ion in solution. I know that's not very impressive when you learned that last year, but guys, that's it. All a substance has to do in order to be an acid is give away hydrogen ions. Now guys, let me throw something your way. It's not in the notes, but maybe we should talk about this. Are you guys comfortable with the idea that when we say hydrogen ions, what we're really talking about is protons? Would it be helpful to draw that so that you really, or do we need to talk about it? You're okay? Don't need to do it? Okay. So guys, the idea here is that hydrogen ions and protons are the same thing. If you're not sure why and you're afraid to ask, I'd love to talk with you about it. Or do you want to ask?
Well, I remember my old school, they said something about like hydronium.
We're not going to do that now. Let me just touch on it briefly. We did do it last year, but the idea is this. When an acid loses hydrogen, and acids are only acids in water. I don't know, guys, we should talk about this. Strong acids, what are they before they go into water? Gases. Weak acids, what are they before they go into water? Solids. They actually all look like table salt, most of them. Matthew, the deal is this. When you then take that acid and put it into water and it dissolves, the hydrogen ions that are released through dissolving do not float around carefree. They actually bond to water and they form this thing called hydronium ion. We'll talk more about that later, but that's actually what's going on. Is that okay? Okay. So guys, what you're going to find out then is that there's two types of acids. Not strong and weak. That is true, but this is a different way to classify acids. Guys, one type of acid is what we call a monoprotic acid. Mono, of course, means one. Protic means proton. So a monoprotic acid is an acid that releases only one hydrogen into solution. An example would be hydrochloric acid, and when it dissociates, it breaks into one hydrogen and one chloride. Now guys, not surprisingly, if we've got monoprotic acids, we also have what are called polyprotic acids, where poly means many, like polygon is many-sided. So a polyprotic acid is an acid that releases more than one proton into solution. Oh, that's interesting. Okay. So guys, you ready for a question? How many of the strong acids are polyprotic? No. Half, 3, 11, 7, hut. How many of the strong acids are polyprotic? All right, let's go through. Oh, there it is. No, there's one. Guys, do this. HCl, 1H. HNO3, 1H. HI, 1. HBr, 1. HClO3, 1. HClO4, 1. H2SO4. There's only one polyprotic strong acid, and that is sulfuric acid, H2SO4. Now, guys, as we move into this thought, then, you need to understand that when these acids release protons, these protonations get progressively weaker. So the first proton that an acid, the polyprotic, gives off is the strongest protonation it will experience. Then the second protonation is weaker, and there could even be a third protonation like H3PO4, and they all get progressively weaker. So guys, here's what I want you to do. Write the balanced equation for the first protonation for sulfuric acid. Do it in your notes. Write the first protonation for sulfuric acid. I've already given you H2SO4, which I shouldn't. But let's write the first protonation. Did you get it? So we've got H2SO4. It releases a proton. And what else is left? HSO4, like so. And you write that down on the test, and I mark the whole thing wrong. Why is that wrong? HSO4 has a -1 charge. if H2SO4 is neutral, and it is, when you pull the positive proton off of H2SO4, the HSO4, which is left over, has a -1 charge. Now guys, with that said, let me show you a little something. Ready? This one's for free. So don't do this in your notes, but cover over the H. I don't know if I can even do that. But if you cover over the H, what's left? Which is what? Sulfate. So guys, ready? If SO4 is sulfate, SO4 with 1 hydrogen added to it is what is called bisulfate. Just so you know, and this you'll pick up on this more later, but if you add a hydrogen to a polyatomic, then the result of that is the bi form of that ion. For example, don't write this down, but for example, guys, what is that? Carbonate. What is this? Bicarbonate. Bond it to sodium and you get sodium bicarbonate, which is what? Baking soda. Okay? So guys, just remember, if you add a hydrogen to something, you add the prefix bi. Doesn't really pertain to what we're doing now though. Okay, so guys, with that said, let's go back up here to our example of our acid and let's play with this. Okay, so there's our first protonation, and that hydrogen pops off. But now, guys, you'll notice that we've got the bisulfate ion left, and that thing still has a hydrogen, and guess what it does to that hydrogen? Releases it. So now, guys, let's write the balanced equation for the second protonation. So now we bring down the HSO4 minus ion, which is the bisulfate ion, and that dude now can release another proton, and when it does, what's left? SO4, 2 minus the sulfate ion. And you write that down on the test, and you get that one wrong too. Why? No, and that's not why. The reason that this is wrong is because this is not a strong step. Now guys, pause. What does strong mean in chemistry? Complete. And we established that second and third protonations get progressively weaker. So this first protonation is a strong, complete protonation. This second protonation is not strong. Instead, it reaches equilibrium. No, it actually does matter, because what you're going to find out, and this seems really nitpicky, but I've seen people get this wrong on the AP test. You cannot do this to represent equilibrium on in the AP test, because you're going to find out in a couple months that is the way that we represent resonance stabilized conformations for resonance stabilized molecules. We'll talk later. What you actually have to draw, and you can do this if you want, or you can do this if you want. The thing that they won't allow is that. Okay? Okay, so guys, with that said, we now understand that these successive protonations are weaker than the original protonation. And so we end up with a mixture of both. You guys good? Yeah? What? Yeah, to some degree or another. Like, for example, if you had H3PO4, by the time that you get down to HPO4 2 minus, that barely breaks apart at all. Yeah. You've been waiting. Go ahead.
So does that make it more acidic?
It does, slightly, because, and guys, so let's think through this. What if you have a 1 molar solution of HCl and a 1 molar solution of H2SO4? Which one is more acidic? And the answer is H2SO4. The reason is because the 1 molar solution of H2SO4 has all of the protons from the first protonation and some more protons from the second protonation. And so when we get into chapter 17, we'll actually talk about how do you calculate the pH of polyprotic acids, and you'll find out we have to actually keep track of both sources of protons. Yep. You guys good? All right, so now guys that we understand these two different types of acids, and this is just what we just wrote down. So guys, let's look at maybe a video that might drive this home a little more clearly, talking about the fundamentals of acids. Here we go.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid.
Don't you wish they could say that about you? You are common and important. Never mind.
When hydrogen chloride gas dissolves in water, it forms
So guys, what's missing from this picture? The water. Right? So really, and we'll talk about this later, but really what's happening is that chloride ion is surrounded by water molecules, just like the chloride that comes off a table salt. And then this hydrogen ion, as Matthew got us thinking again, bonds to water to form H3O. But for now, if you've got this idea, you're just fine.
Chloric acid. Hydrogen chloride is very soluble in water and is completely dissociated.
So guys, let me ask you a question. Will those ever get back together? So assuming we don't evaporate the water, will those ever get back together? They will not. That's what makes HCl a strong acid.
It is therefore a strong electrolyte.
And a strong acid.
Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes.
Will those ever get back together? Strong acid.
Form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it does not completely ionize. It is therefore termed a weak electrolyte.
So this will break apart. But will it necessarily stay separated? No, you'll see in this animation they will come back together. Please don't get the misunderstanding that that means that they will necessarily rebond with the hydrogen they lost. There's hydrogens everywhere from other molecules, and it doesn't have to be the one they lost, but they actually will reform the unprotonated substance. Just a second. Now guys, is this dissolved? Yeah, even in its unprotonated form, it's dissolved. If you get a jug of vinegar, there's no solid on the bottom. It's all dissolved, but not much of it is ionized. That's what makes it weak. Go ahead.
Will they keep breaking and bonding over?
Back and forth and back and forth. But the thing that's interesting, remember the concept of, and so guys, let's talk about this. Brandon said, do they just keep doing this? And the answer is yes. But what they actually do, hey, good to see you. Alyssa, your car's running. Where are you? Yeah. That's interesting. Good to see you. I don't know. Just says your car's running. Do you have your keys? That's really odd. Just a second. So, yeah, go check it out. So he's asking, does this just keep going and keep going and keep it? And the answer is yes. But here's the thing that you need to understand. This reaches equilibrium. And remember, the definition of equilibrium is where the forward and reverse things are happening at the same rate. So what happens is at any given moment, you've got some molecules that are breaking apart, but you've got some molecules that are reforming, but those are happening at the same rate. So the amount of broken apart and unbroken apart molecules is consistent. Is that okay? You good?
So the acetic acid is a weak electrolyte, and a weak acid.
Mm-hmm.
In this, it showed one hydrogen coming off.
Yes.
But the nitric acid that it showed before, it also showed.
Sure. So they're all monoprotic. So these are all monoprotic acids because they only give away hydrogen, one hydrogen. Nitric acid does this strongly. Acetic acid does this weakly, but they're all monoprotic. Go ahead.
Why didn't the whole OH break off?
Because we're going to go all into that in chapter 16. Okay, so now guys, let's talk about bases. Here we go. So when we talk about bases, guys, we are talking about substances that accept protons. And when bases accept protons, this causes the concentration of OH to go up. I know that doesn't make sense, but it will in a minute. Now guys, what you're going to find out is there's actually two types of bases. It's not monobasic, but it's these. We have what are called the metal hydroxide bases. Lithium hydroxide, sodium hydroxide, rubidium, cesium, calcium, strontium, barium. The metal hydroxide bases. These are the substances that contain OH and they release OH into water. But guys, remember, these are lithium, sodium, potassium, rubidium, cesium, calcium, strontium, calcium, strontium, barium hydroxide. What are those? That list of bases that I just read to you, those are the strong bases. These are the strong bases. Then guys, there's a whole nother class of substances that act as bases. These are what are called the non-hydroxide bases. The one that you need to know right now is NH3, which is ammonia. So guys, the non-hydroxide bases react with water by accepting a proton. When they do this, and these are our weak bases. So I'll let you write it down, then we'll talk about it, then we'll watch a video, and then we're going to talk about some specific reactions that you need to know to wrap up the day. So again, guys, I'll let you write it down and then we'll talk. Yeah? That's this. Yep. But doesn't that make sense because this is a weak base? Oh. Oh, it's the best that I could, and actually that's not true anymore. I actually figured out how to put the correct symbol there, but it used to be, that was the only thing I could do, was a less than 2 equals and a greater than. I figured out how to get around that because I'm smart. I just forgot to change it. You're okay. Okay, so guys, let's talk about this. So now we've got this other type of base, which is called a weak base. The one that you need to know right now is NH3. So guys, NH3 is a base, and we know that bases increase the concentration of hydroxide. So now we're saying, wait, how can NH3 make hydroxide if NH3 doesn't contain hydroxide? The answer is by attacking water. And so guys, what you need to remember is that water is H2O, or you can think of water as HOH. And if we can get a substance to come along and steal the H from water, what's left over? OH. And that's what NH3 does. NH3 steals a hydrogen from water, creating NH4+, which you already know is called ammonium ion, and then that kicks out an OH. Guys, this is how the weak bases function as bases. They don't bring OH to the table, they steal hydrogens away from water, and when they do, they turn water into OH. Now guys, understand all of these are weak. So you'll see in the video, they actually will give the H back and turn this back into water, and it looks like this.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common
Strong bases.
When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide...
See it? So guys, here we've got our sodium, here we've got our hydroxide. Will those ever get back together? Strong base.
It is completely ionized in solution. It is referred to as a strong base. It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water,
What's it going to do? It's going to steal hydrogen from the water.
it reacts with water to form the
You see the OH now? But is it going to stay there?
ammonium and hydroxide.
Got it? So guys, when we represent that, we've got to represent it with the equilibrium arrow because it does in fact reach equilibrium. Oh, wow.
So ammonium
Ions
is not a strong base.
It is a weak base.
lies largely to the left.
But understand, ammonia gas is not a base at all. Ammonia gas, which is NH3, only forms a base when it goes into water. Yep. You guys okay? We doing good? All right. So guys, with that said, we now understand the fundamentals of strong acids and strong bases, and we are now ready to start doing some chemistry. So here we go. Guys, you're going to find out that there are some acid-base reactions that you simply need to, you just need to familiarize yourself with. The first of these types of reactions are what we call neutralization reactions. So guys, let's talk about neutralization reactions, and you are going to get to build on what you learned last time. Remember writing net ionic equations, and you're going to have sort of an aha moment as we track this backwards and figure out why we call them neutralization reactions. So what is a neutralization reaction? A neutralization reaction is when an acid and a metal hydroxide base react together to form salt and water. But you'll notice that it's not salt, it's a salt. Because guys, salts, remember, are a positive and a negative ion ionically bonded together. Could.
Like a baking soda and nitric acid, right?
Yep. So guys, if we're not clear on this, when we talk about salts, salts contain a cation, which you'll find out in a minute comes from the base, and they form an anion, which comes from an acid. Okay, so let's do this. Let's take, for example, HCl, strong or weak acid or base? Strong acid. KOH, strong base, right? It's a group 1 potassium hydroxide. So guys, here's what I'd like you to do first. Predict the products. Draw your arrow. By the way, how do I know that this will be a single-headed arrow and not a double-headed equilibrium arrow? Because both of those are strong. Here's the thing that's cool. You're going to love this in chapter 17. Guys, if either one of these is strong, it forces the other one to behave as if it's strong. So if either one of these is strong, it will go to completion. In this case, they're both strong, so we're money. I'm going to give myself a little more space. So we've got HCl, we've got KOH. Guys, first thing we need to do is predict the products. So good. Our first product, and I'll just do this and then erase it. Our first product will be the H hooking up with the OH, which we call water. And then guys, our second product will be the K hooking up with the Cl, which is potassium chloride. So there's our salt. Now guys, you'll notice in reference to this thought, we're okay. Let me do, I think I can do this. Yep, there we go. Okay, so guys, in reference to this thought right here, the cation, the in the salt, the cation came from the base, right? That's where the potassium came from. The anion in the salt came from the acid. That's the Cl. That'll always be the case. Okay. Now with that said, let's balance this. Done? We're done. Okay. So now, guys, this is the kind of neat aha moment. When you are asked to write the balanced equation for the reaction of hydrochloric acid and potassium hydroxide, you will never again write this. You will write the net ionic equation. So guys, let's go through the steps just to make this super clear. But if you can jump right to net ionic, that's great. But let's do this. Ready? So, does hydrochloric acid dissolve in water? Yeah, absolutely. So we're going to write that as H plus Cl minus. Does KOH dissolve in water? All the strong bases dissolve in water. That's what makes them strong bases. So this is K and this is OH. Now, does water dissolve in water? No, because water is water. So we write down water. Now, does KCl dissolve in water? Yeah, because we know that all potassium, all group 1 salts dissolve in water, and all halogen-containing salts dissolve in water unless they're bonded to silver, lead, or mercury. So this also dissolves in water, so we do this. Now, guys, here comes the neat aha moment. Is hydrogen a spectator? No. Is chloride a spectator? Yeah, get rid of it. Is potassium a spectator? Ooh, potassium ion, is it a spectator? Yep. What is our net ionic equation? H plus OH yields water. Now do you understand why we call these neutralization reactions? What is the pH of water? 7, which is neutral. Guys, anytime you have a reaction between a strong acid and a strong base, the net ionic equation is always simply the formation of water. Get it? That's why we call these neutralization reactions. Just a moment. Guys, understand the idea is that the other part of the acid and the base will always be a spectator. You okay? Go ahead.
So ACl doesn't affect pH at all?
No. No, and actually we're going to do, I know I keep saying this, but again, guys, I told you, right, this is a taste, and this is going to be a big unit. We will actually learn to calculate the pH of salt solutions. In this case, the pH of this would be 7. What you'll find out is if these were either a weak acid or a weak base, it would change the pH, and the math behind figuring it out takes about a full page to figure out.
So a strong base and a strong acid always form 2 ions that don't affect.
Exact. Say that again. Let me say it again. So a strong acid and a strong base will always release 2 ions in the salt that will always be spectators, and in chapter 17 you'll find out never affect pH. Yep, go ahead.
You ever have where the salt from the neutralization reaction is a precipitate?
Oh, absolutely. Not today, but yes. Yep.
So then in that case, you wouldn't write it as...
Correct. Then the entire thing would be the net ionic equation. All right. So guys, we are now ready to change the game. An acid-base reaction, but now one of our substances will not be water soluble. Ready? Goes like this. Write this down, word for word. Just because a base is not a strong base, it doesn't mean it isn't a good base. Guys, some of the best bases on the planet are not strong bases. No. Ammonium's weak. Just because it isn't a strong base doesn't mean it isn't a good base. Write it down and we'll talk. Just because it isn't a strong base doesn't mean it isn't a good base. So guys, let's talk. In order for this to make sense, you've got to remember what strong means. It means completely ionizes in water. And guys, here's the deal. Let me show you an example. Write this down with me. Aluminum hydroxide. Does aluminum hydroxide dissolve in water? It does not. Guys, aluminum hydroxide is not a strong base. It's not a strong base because it doesn't dissolve in water. So guys, let's talk. Which hydroxides do dissolve in water? Lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium. That's what makes them the strong bases, because strong simply means completely breaks apart in water. Do you see how that connects? That's why you memorize those. So guys, those are the strong bases. So follow along with me. Is aluminum hydroxide a strong base? No, why not? It doesn't dissolve in water. But guess what? This is a kick-butt base. Guys, when we do acid-base chemistry later in the year, if we need something that will neutralize acid really effectively, that's what we're going to add. Why would this be a really good base? It's got 3 hydroxides. This is an unbelievably good base. It's just not a strong base. Do you see the difference? By the way, guys, where do you find aluminum hydroxide in your day-to-day life? Tums and Rolaids. This is actually the base that they put in antacids because they want to keep the tablets small. And so if they're going to have you eat something that neutralizes your stomach acid, you want it to be a really good base. And so consequently, they use aluminum hydroxide. Anyway, so guys, what you need to be able to do is figure out how this chemistry works. So let's react this with hydrochloric acid. Now guys, what would this reaction look like? If you were to go and do this reaction in lab, what would it look like? What would the hydrochloric acid look like? A liquid in a bottle, right? Hydrochloric acid is water soluble. It's a strong acid. It's a liquid in a bottle. Now guys, what would aluminum hydroxide look like? A white powder. So literally, and you don't need to draw this, but literally what you would do is you would take a pile of aluminum hydroxide, put it in the bottom of a beaker, and then dump hydrochloric acid on it. Can you picture that? Okay, so guys, with that said, let's predict our products. Double displacement reaction, aluminum hooks up with the chlorine, the hydrogen hooks up with the hydroxide, so we get water and we get aluminum chloride. Now guys, we need to balance this. And when I balance these reactions, I prefer to write water as HOH. It makes it easier. So we've got 1 aluminum, we've got 3 OHs. Here we only have 1 OH, so we need a 3. Then we've got 1 hydrogen and we've got 3 hydrogens. And so we need a 3, and then 3 chlorines and 3 chlorines, and that balances. Now guys, check this out. Let's do the net ionic equation without doing any work in between. So guys, let's talk about this. Does this dissolve in water, aluminum hydroxide? No. Does this dissolve in water? It does. So this is really hydrogen ions and chloride ions. Does this dissolve in water? No, it is water. Does this dissolve in water? Aluminum chloride. It does. So this is actually aluminum plus 3 and chlorine minus 1. Does that make sense? Okay, now let's do this. Is this aluminum, starting out, is this aluminum or is this aluminum plus 3? It's just aluminum because it doesn't dissolve in water. So this starts out as aluminum and it ends up as aluminum plus 3. So did the aluminum do chemistry? So it's not a spectator. Here, this is OH tied up in aluminum hydroxide. Here, the aluminum or the hydroxide is tied up in water. Did the hydroxide do chemistry? Yes, so that's not a spectator. What about the hydrogen? Here, the hydrogen is an ion bobbing around in water. Here, it's tied up in water. Did the hydrogen do chemistry? Now here, chlorine is a negative ion floating around in water. Here, the chlorine is a negative ion floating around in water. Did the chlorine do chemistry? It did not. That is your only spectator. So the net ionic equation then is AlOH3 plus 3 protons yields 3 waters and an aluminum, oh my goodness gracious, and an aluminum 3 plus ion. That's the net ionic equation. Your only spectator is chloride. It didn't do chemistry.
Yeah, the aluminum down.
Right, so good. Did you hear that? Guys, the aluminum started out as an antacid tablet, right? And now it's dissolved into the water that was formed by the reaction and the water that the HCl was originally dissolved in. We okay? All right. So guys, we've got 2 more to do and we're done.
So if it dissolves,
If it started out not dissolved, yes. You got it. All right, now guys, we've got to talk about what are called the gas-forming acid-base reactions. And Catherine, this is getting us back to what you talked about. Do they always form solids? And the answer is no. Sometimes these reactions will form gases. So guys, just write this down. When we talk about the gas-forming acid-base reactions, these will always involve a sulfide or a carbonate bicarbonate, one or the other. And now you know what bicarbonate means. And what will happen is this sulfide or this carbonate or bicarbonate will accept protons from an acid. We will do these reactions in lab, but guys, we're going to have to do the first one in a fume hood because the product is hydrogen sulfide gas, which is poisonous. And it smells, it's that rotten egg smell. So we'll do it in the fume hood.
It's poisonous because you said it smells awful.
Well, in low enough concentrations. Okay, so guys, it goes like this. Sulfides first. So an example of this would be this. We are going to take a sulfide-containing salt, sodium sulfide, and we're going to react that with hydrochloric acid. Now guys, sodium sulfide is water soluble. Sodium sulfide dissolves in water. Now let's predict our products. Double displacement reaction, sodium hooks up with what?
should it be sodium chloride?
Oh, thank you. Sorry, thank you. Na2S, sorry. Thank you. So guys, sodium hooks up with the chloride. It makes NaCl. And then the H hooks up with the S. And that makes H2S, which is that horrible hydrogen sulfide gas. So now we need to balance it, and I think we just need that, right? Oh, and then 2 here. Okay. Now, guys, let's talk about spectators. Maybe we should do this just to be clear. So, guys, this is aqueous. This is aqueous. We know that table salt is aqueous. But, guys, H2S is a gas. So here we go. Sodium starts aqueous, ends up aqueous. Spectator? Sodium starts aqueous, ends up aqueous.
Yeah.
Spectator. Sulfide starts aqueous, ends up in a gas. Spectator? No. Hydrogen starts aqueous, ends up in a gas. Spectator? No. Chloride starts aqueous, ends up aqueous. Spectator? Yep. This is the net ionic equation for that reaction. Good? One more to go. Guys, the last thing we need to talk about is when an acid reacts with a carbonate or a bicarbonate. We'll do a bicarbonate, but it doesn't matter. They both work the same. So let's do this. Let's go HCl, and let's react that with, let's just do baking soda, sodium bicarbonate. So guys, this is interesting. You've never seen anything like this. So this is a double displacement reaction. You've seen that, but it's just the beginning of the story. Double displacement reaction, the hydrogen goes with the bicarbonate, and it forms H2CO3. Did you see that? Is that okay? Then, guys, the Na hooks up with the Cl, and that forms sodium chloride. Now, guys, here's the thing that's interesting. Well, let's do this first. Let's narrow this down and let's get rid of the spectators. So hydrogen starts out aqueous and ends up in this acid. It is not a spectator. Chloride starts aqueous and ends up aqueous. Spectator, right? Let me switch colors. Sodium starts aqueous, ends up aqueous, and then bicarbonate ends up in this acid, so it is not a spectator. So guys, our net ionic equation then would appear to be this. But it turns out that's not the net ionic equation. Here's why. That acid, the H2CO3, spontaneously breaks apart. And guys, it actually spontaneously breaks apart into water and carbon dioxide. Ooh, I was thinking carbonate, sorry. To water and carbon dioxide. Now, guys, where does the carbon dioxide go? Off into the air. And as a result, as the carbon dioxide goes away, this can never go backwards. And so this is actually gone, and that is the net ionic equation. Hey, not now. I'm not done with class. No, you need to go. Yeah, I have class right now. You need to go. So, guys, that is the net ionic equation. We've got the H2CO3, which completely breaks apart, and consequently our products are water and carbon dioxide. You get it? Okay. You just need to remember. Yep, you got it. All right. So, guys, with that said, we are now done, and this is your homework for next time. So did I read that wrong? Did he actually look annoyed that I told him he couldn't be in my room during class?